So now let's move to first order differential equations. So an ordinary differential equation in which the independent variable does not appear explicitly is said to be autonomous. So for example, if the symbol x denotes the independent variable, then an autonomous first order differential equation can be written as this form. So for example of an autonomous differential equation is this, where the right hand side does not contain the independent variable x. So unlike this second equation, where the function is now a function of x and y. So we have 0.2 xy. So the zeros of a function, f, for example, we have dy over dx equals to f of y, are of special importance. So a real number c is a critical point of the autonomous differential equation if f of c is equal to 0. So this means that if c is a critical point of the function, then y of x is equals to c is a constant solution of the autonomous differential equation. So a constant solution is also called an equilibrium solution. So for example, if we have the differential equation dp over dt equal to e times a minus bp, so where a and b are constants, this is our example f of p. So finding the critical points, we have p equals to 0 and p is equal to a over b. So now let's move to separable equations. So consider the first order differential equation dy over dx equal to f of x and y when f does not depend on the variable y, that is, f of xy is just equivalent to g of x. The differential equation can be solved by integration. For example, if we have this form, if g of x is a continuous function, then integrating both sides gives this answer, where the capital G of x is just integral of g of x, and then we have plus an arbitrary constant. So for example, we have differential equation dy over dx equal to 1 plus e to the 2x. So this differential equation can be solved directly by using integration. So this is a separable equation. So we have dy, we have 1 plus e to the 2x. Integrating both sides, we have y equivalent to, we have x plus 1 half e to the 2x plus an arbitrary constant c. So a first order differential equation of this form is said to be separable or to have separable variables. Consider the differential equation dy over dx equal to y squared x e to the 3x plus 4y. Let's see if this equation is separable equation. We can factor out x e to the 3x, and we have y squared e to the 4y. This is our g of x, our of y. We're dividing by h of y, you can see a separable equation. We have dy over h of y is equal to dx dx. Or if we denote g of y as 1 over h of y, we have a separable equation dy dy, then gx dx. On this side are the variables y, and this side are the variables x. So solving for separable differential equations, we can rewrite this equation. We have 1 plus x dy equal to y dx. Transposing y to the other side and 1 plus x to the other side, we have dy over y equal to dx over 1 plus x. Integrating both sides, dy over y equal to x over 1 plus x. We have integral of dy over y equivalent to ln of y, and the integral of dx over 1 plus x, so we let du is equals to 1 plus x, or du equivalent to x. We have du over u, so this is equal to ln of u or ln of 1 plus x plus an arbitrary constant. So solving for y, we have y is equal to e to the ln 1 plus c, or can you write this as e to the ln x plus 1 times e to the c. This is equal to x plus 1 times e to the c, or we can replace e to the c as another constant, equal to c times x plus 1. The next example is an initial value problem. We have e to the x dx minus y dy equal to 0, where y of 0 is equal to 1. So solving for differential equation, we have e to the x dx equal to y dy. Y squared over 2 equal to e to the x plus constant c, or y squared is equal to 2e to the x plus 2c. Simply write as 2e to the x plus c. Now applying the initial value and solve for the value of c. So y of 0 is equal to 1. We have 1 squared equal to 2e to 0 plus c. Our c is equal to -1. We have y squared is equal to 2e to the x minus 1, or you can write this as y is equal to square root of 2e to the x minus. The next example, we also have an initial value problem. We have y prime is equal to y times quantity x minus 1 squared over y plus 3, where y of 3 is equal to -1. So we can rewrite y prime as dy over dx equal to y times x minus 1 squared over y plus 3. We have y plus 3 over y dy is equal to x minus 1 squared dx. Now we can rewrite this equation on the left hand side as 1 plus 3 minus 3 over y dy equal to x minus 1 squared dx. Now we can integrate both sides. We have y plus 3 ln of y equal to, so we can let u is equal to x minus 1, du is just dx. We have integral of u squared du is equal to 1/3 u to the u cube plus an arbitrary constant. So this is y plus 3 ln of y equal to 1/3 of 1/3 times x minus 1 cube plus c. So this equation is an implicit solution, since we cannot solve for y as an explicit expression of x, but we can solve for the value of c. So y of 3 equal to 1. We have 1 plus 3 ln of 1 equal to 1 over 3, 3 minus 1 cube plus c. This is -1. So ln of -1 is 0. We have -1 equal to 1/3 2 cube plus c. Solving for the value of c, we have -11 over 3. Solution is y plus 3 ln of y equal to 1/3 x minus 1 cube minus 11 over 3. Solutions defined by integral. If g is a function continuous on an open interval I containing a, then for every x in I, we have derivative of this term with respect to x. We have the integral of g of t dt evaluated from a to x is equivalent to g of x. So for a simple initial value problem, for example, we have dy over dx equals to g of x, where we are given the initial value y of x naught is equal to y naught. So the solution is y of x is equal to the initial value plus the integral of g of t dt evaluated from x naught to x. Example number 4, we have x cosine of x dx plus quantity 1 minus 6y to the 5th dy is equal to 0, where y of pi is equal to 0. This initial value problem, our x0 is equal to pi, and our y0 is equal to 0. You can evaluate this differential equation by integrating both sides. X cosine of x dx plus 1 minus 6y to the 5th dy equal to 0. You can evaluate this term right here from pi to x, and this term from 0 to y. You can solve this term using integration by parts. So integration by parts. Integration by parts, we have u v minus integral of v d u. Let's assign u as x. We have du is equal to dx, or dv equal to cosine of x dx, or v equal to sine of x. We have uv, we have x sine of x minus integral of v du. We have sine of x and dx is equal to x sine of x plus cosine of x. We have x sine of x plus cosine of x evaluated from pi to x plus of the integral of this term, we have y minus y to the 6th evaluated from 0 to y equal to 0. We have x sine of x plus cosine of x minus, we have pi sine of pi plus cosine of pi. We have y to the 6th minus y. Sine of pi is equal to 0, and cosine of pi is negative 1. We have x sine of x plus cosine of x plus 1 equal to y to the 6th minus y. We have our final answer.